Hello there, and welcome to a journey through the most soothing mysteries of our cosmos. I'm so glad you found your way here tonight. Tonight, we're going to drift through some of the most calming and beautiful truths about our universe. Not the explosive supernovas or crushing black holes that might keep you awake, but the quiet wonders, the gentle rhythms, and the peaceful processes that have been unfolding for billions of years while you sleep. These are the cosmic lullabies that space whispers to itself in the darkness between stars. Some of what you'll hear tonight might surprise you with its gentleness. Other facts will simply wash over you like waves on a distant shore, carrying you closer to rest with each passing moment. And if these peaceful explorations help you unwind or give your restless mind something beautiful to contemplate, consider subscribing to join others who find comfort in the quiet corners of science. Space is mostly made of nothing, and that nothing is perfectly peaceful. When we think about the universe, we often picture blazing stars and swirling galaxies, but the truth is far more serene. The vast majority of space is empty, filled with a tranquil silence that has existed for billions of years. This emptiness isn't harsh or cold in the way we might imagine. It's simply quiet, like the deepest meditation you've ever experienced. In this cosmic silence, there are no sounds because there's no air to carry them, no traffic, no machinery, no voices. Just perfect, absolute quiet, stretching for millions upon millions of miles in every direction. Even light travels through this space without disturbing its fundamental peace, moving in straight lines through the gentle void like thoughts drifting through a calm mind. This peaceful emptiness isn't actually empty at all, but filled with something even more soothing than nothing. It contains the faintest whisper of energy, a background hum so gentle it takes our most sensitive instruments to detect it. This is the leftover warmth from the very beginning of everything, now cooled to just a few degrees above absolute zero. It's like the universe's own gentle breathing, so soft and steady that it creates the most perfect ambient temperature for cosmic rest. The moon dances in slow motion around our world. Every night when you look up at the moon, you're watching one of nature's most calming performances. Our lunar companion moves through space at about 1 kilometer per second, which sounds fast until you realize this creates the slowest, most graceful dance imaginable. It takes the moon an entire month to complete one gentle orbit around Earth, tracing the same peaceful path it has followed for over 4 billion years. This celestial waltz is so reliable, so perfectly predictable, that ancient civilizations used it to mark time and seasons. The moon's gentle gravitational pull creates our ocean tides, a rhythm so steady and soothing that it has become the heartbeat of our planet. Twice each day, the waters rise and fall in perfect synchronization with our moon's position, creating a cosmic breathing pattern that has continued uninterrupted since long before life began on Earth. What makes this even more peaceful is knowing that this dance is gradually slowing down. The moon is very slowly moving away from Earth, just a few centimeters each year. This means that billions of years ago, the moon appeared larger in the sky, and billions of years from now, it will appear smaller. But this change is so gentle, so gradual, that thousands of human generations will see exactly the same moon you see tonight. hanging peacefully in the darkness above. Light travels at the most constant speed in the universe. There's something deeply comforting about knowing that light always moves at exactly the same speed through empty space, no matter where it comes from, no matter where it's going. Light maintains this perfect consistency. It's like the universe's own speed limit, a cosmic constant that never varies, never changes, never breaks down. This means that the light from distant stars has been traveling towards you at this same steady pace for years, decades, centuries, or even millennia. The gentle starlight you see tonight left those distant suns long ago and has been making its way to you through the peaceful darkness of space. Never hurrying, never slowing, just maintaining its perfect, unhurried journey across the cosmos. When you look up at the stars tonight, you're not just seeing distant suns, you're seeing ancient light that has traveled unimaginable distances to reach your eyes. Some of that light began its journey before your grandparents were born. Some started traveling before humans ever walked the earth, and all of it arrived at your exact location tonight, at the exact moment you chose to look up, as if the universe had been planning this gentle meeting between you and the stars for longer than you can imagine. Planets orbit in perfect harmony like a cosmic symphony. Our solar system operates like the most peaceful orchestra ever assembled, with each planet maintaining its own rhythm while contributing to a greater celestial harmony. Mercury completes its quick waltz around the Sun in just 88 Earth days, while distant Neptune takes a leisurely 165 Earth years to complete one gentle orbit. These orbital periods create what astronomers call celestial mechanics, but what we might better understand as cosmic music. Each planet plays its own note in this vast symphony, and together they create patterns and harmonies that have been playing for over 4.5 billion years without missing a single beat. What's even more soothing is that these orbits are incredibly stable. Despite the vast distances and enormous speeds involved, each planet knows exactly where it's supposed to be at any given moment. Earth arrives at the same point in its orbit every year on your birthday, creating the gentle rhythm of seasons and the reliable passage of time that gives structure to our lives. The gravitational forces that maintain these orbits work like invisible strings, connecting each planet to the sun and to each other. These forces are always perfectly balanced, always exactly right, creating a cosmic dance so stable and predictable that we can calculate exactly where each planet will be thousands of years into the future. Stars are born in the most gentle nurseries imaginable. When we think about star formation, we might imagine violent explosions or dramatic cosmic events. But the truth is far more peaceful. Stars are born in vast, quiet clouds of gas and dust that drift through space like cosmic fog. These stellar nurseries are among the most tranquil places in the universe, where the only sound would be absolute silence, and the only movement is the gradual, gentle collapse of gas under its own gravity. This process takes millions of years to complete, unfolding so slowly and gently that if you could watch it happen, it would be like observing the most patient meditation in existence. Tiny particles of dust and gas slowly come together, attracted by the weakest possible gravitational forces. gradually building up density over time scales that dwarf human civilization. As these cosmic clouds slowly contract, they begin to warm up. But even this heating is gradual and gentle. For most of a star's formation process, these protostars are cooler than a summer day on Earth, glowing only faintly in infrared light that our eyes cannot see. They're like cosmic embers slowly warming up over geological time, taking millions of years to reach the point where they can begin to shine with their own light. When nuclear fusion finally begins in the core of a new star, it doesn't happen with a bang or an explosion. Instead, it's like the gentlest possible ignition, a cosmic pilot light that will burn steadily for billions of years. Our own sun has been burning with this same gentle nuclear fire for nearly 5 billion years, and it will continue burning peacefully for another 5 billion years, providing the steady, reliable warmth that makes life on Earth possible. The universe expands in perfect slow motion. One of the most peaceful aspects of our cosmos is that the entire universe is slowly expanding, carrying galaxies away from each other at a rate so gradual that it's completely imperceptible in human lifetimes. This cosmic expansion has been happening for nearly 14 billion years, and it continues today with the gentlest possible acceleration. This expansion doesn't mean that galaxies are racing away from each other through space. Instead, space itself is slowly growing larger, like a balloon being inflated in slow motion. The distances between galaxies increase gradually over millions of years, creating more room in the universe for new structures to form and new possibilities to emerge. What makes this expansion particularly soothing is its uniformity. It's not chaotic or random, but perfectly smooth and predictable. Every region of space expands at the same rate, maintaining the same proportions and relationships that have existed since the early universe. It's like the cosmos is slowly stretching itself, taking a deep breath that has been lasting for billions of years. This gentle expansion also means that the universe is becoming more peaceful over time. As galaxies move farther apart, the night sky will gradually become darker and quieter. In the far future, beings looking up at the stars will see fewer galaxies and more empty space, creating an even more serene cosmic environment than we enjoy today. Gravity works like the universe's gentle embrace. We often think of gravity as a force, but Einstein showed us something more beautiful. Gravity is actually the curvature of space and time itself, created by the presence of matter and energy. This means that massive objects like stars and planets create gentle depressions in the fabric of reality, and smaller objects naturally follow the curved paths created by these depressions. This creates what we might think of as the universe's most tender embrace. Every object with mass reaches out through space and time, creating a field of gentle attraction that extends infinitely in all directions. You are held to the earth, not by chains or ropes, but by this cosmic embrace that connects you to every particle of matter in the planet beneath your feet. This same gentle embrace extends throughout the solar system and beyond. The moon is held in its orbit by Earth's gravitational embrace, while Earth and all the other planets are embraced by the sun's much larger gravitational field. The sun itself, along with hundreds of billions of other stars, is held in the gentle gravitational embrace of our entire galaxy. Even more remarkable is that this gravitational embrace operates at the speed of light, which means that changes in gravity propagate through space as gentle waves called gravitational waves. These ripples in space-time itself pass through the universe like the gentlest possible vibrations, so subtle that we've only recently developed instruments sensitive enough to detect them. When they pass through your body, they stretch and compress you by distances smaller than the nucleus of an atom, creating the most delicate massage imaginable at the deepest level of reality. Time flows differently throughout the cosmos. Perhaps one of the most peaceful aspects of the universe is that time itself is not rigid or absolute, but flows like a gentle river that moves at different speeds in different places, near massive objects like stars and planets. Time flows slightly slower than it does in the empty spaces between them. This means that time itself participates in the cosmic dance, speeding up and slowing down in harmony with the distribution of matter and energy throughout the universe. This temporal flexibility means that there's no single universal now that applies everywhere in the cosmos. Instead, each point in space has its own gentle flow of time, creating a universe where simultaneity is relative and the present moment is always personal and local. What makes this even more soothing is the realization that this time dilation effect means that the universe naturally creates peaceful refuges where time moves more slowly. If you could somehow visit a location far from any massive objects, in the quiet emptiness between galaxies, time would flow slightly faster for you than it does here on Earth. Conversely, near massive objects, time slows down, creating natural sanctuaries where moments last a little longer, and the universe seems to take a deeper breath. This means that the universe itself has built-in meditation retreats, places where time naturally moves at a more peaceful pace. Even here on Earth, time flows slightly slower at sea level than it does on mountaintops, creating imperceptible but real variations in the speed of experience based on your location in the gravitational field. The universe breathes through cycles that span billions of years. Just as you have a natural rhythm of breathing in and out, the cosmos has its own gentle respiratory cycle that unfolds over timescales beyond human imagination. Stars are born, live their lives, and eventually return their material to space in a process so gradual and peaceful that each breath of the universe lasts longer than entire geological eras on Earth. When massive stars reach the end of their lives, they don't simply disappear. Instead, they gently exhale their outer layers into space, creating beautiful nebulae that drift through the galaxy like cosmic clouds. These stellar exhalations contain all the heavy elements that were forged in the star's core during its lifetime, including the carbon, oxygen, and iron that make life possible. This material spreads slowly through space, eventually becoming part of new stars, new planets, and perhaps new forms of life. This cosmic breathing cycle means that the atoms in your body have participated in this universal respiration many times. The calcium in your bones may have been exhaled by a star that died billions of years ago, drifted peacefully through space for eons, and eventually found its way into the cloud of gas and dust that formed our solar system. You are literally made of stardust that has been breathing with the universe for longer than Earth has existed. Even more peaceful is the knowledge that this breathing will continue for trillions of years into the future, long after our sun has gently expanded into a red giant and slowly shed its outer layers. The elements it created will join this cosmic respiratory system, eventually becoming part of new stars and new worlds in a future so distant that it's beyond our ability to imagine. Dark matter moves through everything with perfect gentleness. Throughout the universe, there exists a form of matter so peaceful that it barely interacts with anything else. Dark matter makes up most of the matter in the cosmos. Yet it's so gentle that trillions of dark matter particles pass through your body every second without you feeling even the slightest sensation. This invisible matter doesn't emit light, doesn't absorb light, and doesn't reflect light. It simply exists in a state of perfect transparency, influencing the universe only through its gravitational effects. Dark matter particles are like cosmic ghosts, present everywhere but touching nothing, creating the invisible scaffolding that holds galaxies together while remaining completely imperceptible to our senses. What makes dark matter particularly soothing is its stability. While ordinary matter can be heated, cooled, compressed, or scattered, dark matter maintains its peaceful disposition regardless of conditions. It doesn't form stars that explode, doesn't create turbulence or chaos, and doesn't undergo the violent transformations that characterize ordinary matter. Instead, it provides a calm, steady background presence that has helped shape the universe's largest structures with quiet persistence over billions of years. The dark matter in our own galaxy forms a vast, spherical halo that extends far beyond the visible stars. This invisible embrace surrounds us completely, providing the gravitational framework that keeps our galaxy stable and peaceful. As we orbit the center of the Milky Way, we're swimming through this ocean of dark matter like fish moving through perfectly still water, unaware of the medium that surrounds us, but benefiting from its gentle, stabilizing presence. Cosmic background radiation wraps the universe in warmth. Filling every corner of the universe is the gentlest possible form of electromagnetic radiation, the leftover glow from the very beginning of everything. This cosmic microwave background radiation is like the universe's own body heat, maintaining a temperature of just 2.7 degrees above absolute zero throughout all of space. This ancient warmth has been cooling and stretching for nearly 14 billion years, but it still provides a subtle cosmic comfort that pervades everything. No matter how far you might travel into the depths of space, you would never find a place that's completely cold. This background radiation ensures that the universe always maintains this barely perceptible warmth, like a cosmic blanket that covers everything with the most delicate possible embrace. The patterns in this background radiation are incredibly smooth and uniform, varying by only tiny amounts across the entire sky. These gentle variations represent the seeds from which all the structure in the universe eventually grew, but they're so subtle that they create the most peaceful possible template for cosmic evolution. It's as if the universe began with the softest possible whisper, and everything that followed grew from that initial moment of perfect tranquility. When radio telescopes detect this background radiation, they're essentially listening to the echo of creation itself, stretched and cooled until it becomes the most gentle hiss imaginable. This cosmic static has been traveling through space for longer than atoms have existed, carrying with it the memory of a time when the entire universe was as warm and bright as the surface of a star, now cooled to the temperature of liquid helium and spread throughout all of space like the most peaceful possible lullaby. Galaxies rotate like massive, slow-motion whirlpools. Our own Milky Way galaxy is spinning, but so slowly and gracefully that it takes over 200 million years to complete one rotation. This means that since the time of the dinosaurs, our galaxy has turned only slightly more than once, creating a rhythm so stately and peaceful that entire geological eras pass between one galactic season and the next. This rotation isn't chaotic or turbulent, but follows elegant spiral patterns that have been maintained for billions of years. The spiral arms of our galaxy move through space like gentle waves, compression zones where gas and dust collect to form new stars. These waves move at a different speed than the stars themselves, create a cosmic pattern that persists even as individual stars drift in and out of the spiral structure over millions of years. As our solar system orbits the galactic center, we move up and down through the galactic disk in a gentle oscillation that takes about 60 million years to complete. This means we periodically rise above and below the main plane of the galaxy, experiencing different cosmic environments as we follow our peaceful path through space. Sometimes we're in the thick of the galactic disk, surrounded by more stars and cosmic dust. Other times we're in the quieter regions above or below the main disk, where space is more empty and serene. This galactic breathing motion creates natural cycles in our cosmic environment that are so gradual, they're completely imperceptible to human civilization. Yet they may influence everything from the formation of new stars to the evolution of life on Earth. We're passengers on a planet that orbits a star that follows a gentle, undulating path through a galaxy that rotates with perfect cosmic patience, creating layers of peaceful motion that stack together like the most complex and beautiful slow-motion dance ever choreographed. The space between stars is filled with the thinnest possible mist. The interstellar medium, the space between stars, isn't actually empty, but contains an incredibly thin distribution of gas and dust. This cosmic mist is so tenuous that it contains only about 1 atom per cubic centimeter, making it a better vacuum than anything we can create in laboratories on Earth. Yet it still provides a subtle medium through which starlight travels. This interstellar material moves in gentle currents and flows, stirred by stellar winds and the slow rotation of the galaxy. Sometimes these movements compress the gas into denser regions where new stars can eventually form. But most of the time, the interstellar medium simply drifts through space like the most delicate fog imaginable, so thin that you could travel through it for years without noticing its presence. The dust grains in this cosmic mist are smaller than the particles in cigarette smoke, and they're spread so far apart that each grain is typically separated from its neighbors by distances comparable to the size of Earth's orbit around the Sun. Yet over the vast scales of interstellar space, this incredibly sparse material creates beautiful structures, nebulae that glow softly in the light of nearby stars, or appear as dark silhouettes against the brighter regions of the galaxy. This interstellar medium also carries magnetic fields that thread through the galaxy like invisible ribbons, guiding the motion of charged particles and creating order in the seemingly empty spaces between stars. These magnetic fields are incredibly weak by terrestrial standards, thousands of times weaker than Earth's magnetic field. Yet they extend across such vast distances that they help organize the structure of entire spiral arms, creating cosmic scale patterns with the gentlest possible touch. Pulsars keep perfect time across the galaxy. Among the most peaceful objects in the universe are pulsars, the ultra-dense remnants of massive stars that have collapsed into neutron stars and now rotate with incredible precision. These cosmic lighthouses send out beams of radiation that sweep across space like the most reliable metronomes ever created, some of them keeping time more accurately than the best atomic clocks on Earth. A typical pulsar is only about 20 kilometers across, roughly the size of a city. Yet it contains more mass than our entire sun, compressed into a sphere so dense that a teaspoon of its material would weigh as much as a mountain. Despite this extreme density, pulsars rotate with perfect smoothness, some spinning hundreds of times per second, while maintaining their timing accuracy to within nanoseconds over periods of many years. The radio pulses from these neutron stars travel across the galaxy at the speed of light, creating a network of cosmic timing signals that permeate our region of space. As these pulses pass through the interstellar medium, they interact with the thin gas and magnetic fields between stars, creating subtle effects that allow astronomers to map the invisible structure of our galaxy with extraordinary precision. What makes pulsars particularly soothing is their reliability. While most astronomical objects change and evolve over time, pulsars maintain their precise timing for millions or even billions of years. They're like cosmic pendulums that keep swinging with perfect regularity, creating a background rhythm that gives structure to our galaxy's rotation and provides a steady heartbeat for the cosmos that never varies, never falters, and never stops. Comets carry water and organic molecules on gentle journeys. In the outer reaches of our solar system, billions of comets drift in slow, peaceful orbits, carrying within their icy cores the ingredients that may have helped bring life to Earth. These cosmic snowballs follow elliptical paths that take them on gentle journeys lasting thousands or millions of years, occasionally bringing them close enough to the sun to create the beautiful glowing tails that have inspired wonder throughout human history. Each comet is like a time capsule from the early solar system, preserving water ice, carbon dioxide, and complex organic molecules in a deep freeze that has lasted for over 4 billion years. When comets approach the sun, these materials slowly sublimate into space, creating the characteristic coma and tail that make comets visible from Earth. This process is so gradual and gentle that a single comet can survive dozens of passages near the sun before finally exhausting its volatile materials. The water vapor and organic compounds released by comets spread throughout the inner solar system, eventually raining down on planets and moons as a gentle cosmic precipitation that has been falling for billions of years. Some scientists believe that much of Earth's water may have been delivered by comets in the early days of the solar system, making these icy visitors from the outer reaches the bearers of one of the most essential ingredients for life. As comets follow their peaceful orbits through space, they occasionally interact with each other through gravitational influences so gentle that they can take millions of years to change a comet's path significantly. This creates a vast, slow-motion ballet in the outer solar system, where countless icy bodies follow complex gravitational choreography that has been evolving since the solar system first formed, creating patterns of motion so subtle and gradual that they represent some of the most patient dynamics in nature. The solar wind creates the gentlest breeze in existence. Streaming out from our sun at all times is an invisible river of charged particles that flows through the entire solar system at speeds of several hundred kilometers per second. Yet despite these seemingly high velocities, the solar wind is so incredibly thin that it creates the most delicate breeze imaginable, far gentler than the softest whisper of air you've ever felt on Earth. This cosmic breeze carries with it the sun's magnetic field, creating what scientists call the heliosphere, a vast bubble of solar influence that extends far beyond the orbit of Pluto. Within this bubble, we're constantly bathed in this tender solar exhalation, though it's so subtle that we never feel its presence. The solar wind is composed primarily of protons and electrons that have escaped from the sun's outer atmosphere, traveling outward in all directions like an expanding sphere of the gentlest possible cosmic breath. When this solar wind encounters planets with magnetic fields, it creates some of the most beautiful and peaceful phenomena in the solar system. On Earth, interactions between the solar wind and our magnetosphere produce the aurora, those shimmering curtains of light that dance silently in polar skies. These displays represent the visible signature of our planet's magnetic field, gently deflecting the solar wind around us, creating a protective cocoon that shields us from more intense cosmic radiation. The solar wind also shapes the tails of comets, always pushing them away from the sun regardless of the comet's direction of travel. This creates the ethereal, flowing appearance of comet tails, which aren't trails left behind by the comet's motion, but rather streams of material being gently carried away by this constant solar breeze. Even in the depths of space, far from any planet or moon, this solar wind continues flowing outward, carrying with it the subtle influence of our star to the very edges of the solar system and beyond. Moons orbit their planets in perfect gravitational harmony. Throughout our solar system, dozens of moons dance around their parent planets in orbital relationships so stable and predictable that they've maintained their cosmic choreography for billions of years. These natural satellites follow paths that are mathematically precise, creating celestial clockwork that operates with perfect reliability across vast spans of time. Some moons, like Europa around Jupiter, are locked in what's called tidal synchronization, where the same face always points toward their planet. This creates a permanent day side and night side on the moon, with the planet hanging motionless in the sky from the perspective of anyone standing on the moon's surface. This synchronization isn't forced or violent, but represents a natural equilibrium that develops gradually over millions of years as tidal forces gently adjust the moon's rotation. Jupiter's 4 largest moons perform an especially elegant dance called orbital resonance, where their orbital periods are related by simple mathematical ratios. For every 4 orbits that Io completes around Jupiter, Europa completes exactly 2, and Ganymede completes exactly 1. This creates a repeating pattern of gravitational influences that has remained stable for billions of years, demonstrating how celestial mechanics can create harmony on the grandest possible scales. Even more remarkable are the shepherd moons of Saturn, tiny natural satellites that orbit just inside and outside the planet's rings, using their gentle gravitational influence to keep the ring particles organized in sharp, well-defined bands. These small moons act like cosmic gardeners, patiently maintaining the structure of Saturn's ring system through gravitational forces so subtle that they work over timescales of millions of years, creating and maintaining some of the most beautiful structures in the solar system through nothing more than patient, persistent gravitational guidance. Planetary rings flow like rivers of ice and rock. The magnificent ring systems around the giant planets represent some of the most peaceful and hypnotic motions in the solar system. These rings aren't solid structures, but countless individual particles, each following its own gentle orbit around the planet. From a distance, these particles create the appearance of solid rings, but up close, they reveal themselves to be vast rivers of cosmic debris flowing in perfect synchronization. Saturn's rings, the most spectacular example, contain billions of ice particles ranging in size from tiny grains to house-sized boulders, all orbiting the planet at slightly different speeds depending on their distance from Saturn's center. This creates a shearing motion where inner particles gradually overtake outer ones, like cars moving at different speeds in adjacent lanes on a cosmic highway. Yet this differential motion is so gradual and gentle that the rings maintain their overall structure for millions of years. The ring particles occasionally collide with each other, but these collisions are typically so gentle that they barely disturb the particles' motions. Instead of violent crashes, these encounters are more like cosmic kisses, where particles briefly touch and then continue on their separate paths. Sometimes these collisions cause particles to stick together temporarily, forming larger clumps that eventually break apart again, creating a constant cycle of aggregation and disaggregation that plays out over decades or centuries. Gravitational resonances with nearby moons create gaps and divisions in the rings, regions where particles are gradually nudged into different orbits through repeated gentle gravitational tugs. These processes work so slowly that they're essentially imperceptible. Yet over long periods of time, they sculpt the rings into intricate patterns of bands and divisions, creating cosmic architecture through the most patient possible application of gravitational forces. Binary stars waltz through space in eternal partnership. Throughout the galaxy, more than half of all stars exist not as solitary suns like ours, but as members of binary or multiple star systems where 2 or more stars orbit around their common center of mass. These stellar partnerships represent some of the most graceful dances in the universe, with stars that may be separated by distances comparable to our entire solar system, maintaining their orbital relationship for billions of years. In these systems, each star follows an elliptical path around the system's center of gravity, sometimes approaching closer to its companion and sometimes moving farther away, but always maintaining the same overall orbital period. Some binary stars are so close that they complete their mutual orbit in just a few hours, while others are so widely separated that they take thousands of years to complete one orbital cycle. The gravitational interaction between binary stars creates tidal effects similar to those between Earth and the Moon. But on a stellar scale, these tidal forces can cause the stars to become slightly egg-shaped, stretched along the line connecting them to their companion. In some cases, these tidal effects are strong enough to cause one star to transfer material to its companion, creating streams of stellar plasma that flow from one star to another in graceful arcs. What makes binary star systems particularly peaceful is their stability. Once established, these orbital relationships can persist for the entire lifetimes of both stars, creating cosmic partnerships that last for billions of years. The stars age together, evolve together, and sometimes even die together, maintaining their celestial waltz from the time of their formation until the end of their nuclear burning phases. Nebulae glow with the softest possible light. Scattered throughout the galaxy are vast clouds of gas and dust called nebulae, some of which glow with ethereal light that represents some of the gentlest illumination in the universe. These cosmic clouds are often hundreds of light years across, yet they shine so softly that they're barely visible to the naked eye, despite containing enough material to form thousands of stars. The light from emission nebulae comes from hydrogen gas that has been energized by ultraviolet radiation from nearby hot stars. This process, called fluorescence, causes the hydrogen atoms to absorb high-energy ultraviolet light and re-emit it as visible red light. The result is a diffuse glow that can persist for millions of years, creating some of the most beautiful and serene sights in the galaxy. Reflection nebulae shine with an even gentler light, created when starlight scatters off tiny dust grains suspended in space. These nebulae typically appear blue because the dust particles scatter blue light more efficiently than red light. The same process that makes Earth's sky appear blue during the day. The scattered light is incredibly soft and diffuse, creating cosmic clouds that seem to glow with their own inner light, even though they're simply reflecting the illumination from nearby stars. Dark nebulae represent perhaps the most peaceful type of interstellar cloud. Dense concentrations of dust that block the light from stars behind them, creating dark silhouettes against the brighter background of the galaxy. These dark clouds aren't empty voids, but regions where future stars will eventually form. Cosmic nurseries that are currently in a state of perfect quiet, waiting patiently for gravitational collapse to begin the slow process of stellar birth. The cosmic web connects everything through invisible threads. On the largest scales, the universe organizes itself into a vast network called the cosmic web, where galaxies are connected by filaments of dark matter and ordinary matter that stretch across billions of light years. This structure resembles a three-dimensional spider's web, with dense nodes where galaxy clusters form connected by thinner filaments that contain fewer galaxies and more empty space. These cosmic filaments aren't visible to our telescopes because they consist primarily of dark matter and hot, diffuse gas. but their presence can be inferred from the way galaxies are distributed throughout space. Rather than being scattered randomly, galaxies tend to lie along these invisible threads, creating a pattern that reveals the underlying structure of the cosmic web. The formation of this web-like structure happened gradually over billions of years, as gravitational forces slowly pulled matter together along the paths of least resistance. This process was so gentle that it didn't disrupt the overall smoothness of the universe, but instead enhanced the subtle variations that existed in the early cosmos, amplifying them slowly until they became the large-scale structure we observe today. Within this cosmic web, matter flows along the filaments like water flowing through the channels of a vast river delta. Galaxies that lie along these filaments can receive a steady supply of fresh gas and dark matter from the cosmic web, feeding their continued star formation and growth. This creates a universe-wide circulation system where matter moves from the sparse regions between filaments into the denser nodes where galaxy clusters form, maintaining cosmic-scale currents that have been flowing for billions of years. Magnetospheres create invisible shields around worlds. Many planets and moons throughout the solar system are surrounded by invisible magnetic bubbles called magnetospheres, created by the interaction between their magnetic fields and the solar wind. These magnetic shields deflect most of the charged particles streaming from the sun, creating safe havens where atmospheres can persist and life can potentially flourish. Earth's magnetosphere extends far into space, creating a teardrop-shaped region of magnetic influence that stretches from about 10 Earth radii on the sunward side to hundreds of Earth radii in the tail that streams away from the sun. Within this magnetic cocoon, we're protected from the full intensity of solar radiation and cosmic rays, allowing our atmosphere to remain stable over geological time periods. The boundary of the magnetosphere, called the magnetopause, represents a delicate balance between the outward pressure of the planet's magnetic field and the inward pressure of the solar wind. This boundary is constantly shifting and rippling as variations in the solar wind cause it to compress and expand. But these changes are typically so gradual that they maintain the overall protective effect of the magnetic shield. Other planets with strong magnetic fields, like Jupiter and Saturn, have even more extensive magnetospheres that can capture and trap charged particles from space, creating radiation belts that spiral around the planet following magnetic field lines. These trapped particles can persist for years or even decades, creating invisible rivers of charged particles that flow around the planet in complex patterns determined by the geometry of the magnetic field. Exoplanets drift in distant solar systems beyond our reach. Throughout the galaxy, thousands of planets orbit stars other than our Sun, each following its own peaceful path through space in solar systems that may be completely different from our own. These exoplanets range from massive gas giants larger than Jupiter to small rocky worlds that might be similar to Earth, all maintaining their orbital stability across the vast distances of interstellar space. Some exoplanets orbit their stars in just a few days, so close to their parent star that their surfaces are heated to thousands of degrees. Others follow distant orbits that take hundreds or thousands of years to complete, spending most of their time in the cold, dark regions of their solar systems, where temperatures approach absolute zero. Yet regardless of their orbital characteristics, each of these distant worlds maintains its celestial dance with the same gravitational precision that governs the planets in our own solar system. Many exoplanets exist in systems with multiple planets, creating complex gravitational interactions that can lead to orbital resonances and other harmonic relationships similar to those found in our solar system. Some systems contain planets that are tidally locked to their stars, with permanent day and night sides, while others have planets with highly elliptical orbits that experience extreme seasonal variations as they swing from close approaches to distant separations from their parent stars. The discovery of these distant worlds reminds us that the peaceful orbital mechanics we observe in our solar system are replicated throughout the galaxy on an enormous scale. Each star system represents its own unique solution to the gravitational dance between stars and planets, creating billions of variations on the theme of celestial harmony that plays out across the galaxy in systems so distant that their light takes years, decades, or centuries to reach us. Brown dwarfs burn with the gentlest nuclear fires. Between the smallest stars and the largest planets exist objects called brown dwarfs, sometimes referred to as failed stars, because they never became massive enough to sustain the nuclear fusion reactions that power true stars. Instead, these intermediate objects glow with the faintest possible stellar light, burning deuterium and lithium in their cores at rates so slow that they can maintain their gentle nuclear fires for billions of years. Brown dwarfs represent stellar minimalism, objects that contain just enough mass to initiate nuclear reactions, but not enough to burn hydrogen efficiently like our Sun. Their surface temperatures are typically cooler than the flames of a candle, making them among the coolest objects that can still be considered stars. They emit most of their energy in infrared wavelengths, glowing with a deep red light that's barely visible to human eyes. These objects age very slowly, gradually cooling and fading over periods that exceed the current age of the universe. Unlike more massive stars that burn through their nuclear fuel relatively quickly and then undergo dramatic changes as they evolve, brown dwarfs settle into a steady state of gentle cooling that can continue for trillions of years, making them among the most stable and long-lived objects in the galaxy. The existence of brown dwarfs demonstrates that stellar formation is a continuous process rather than a binary choice between planet and star. These objects fill the gap between the largest planets and the smallest stars, showing us that the universe creates objects of every possible mass, and that even the gentlest nuclear burning can sustain an object's glow across cosmic timescales that dwarf the lifetime of more energetic stars. White dwarf stars cool like cosmic embers for billions of years. When stars like our Sun reach the end of their nuclear burning phase, they shed their outer layers and leave behind a white dwarf, a stellar remnant that's roughly the size of Earth but contains about as much mass as the Sun. These incredibly dense objects represent the final resting state for most stars in the galaxy. Glowing with leftover heat from their former stellar lives, while slowly cooling over periods that span hundreds of billions of years. White dwarfs don't generate new energy through nuclear fusion, so they shine only with the thermal radiation left over from their formation. This makes them stellar fossils, objects that preserve the memory of their parent star's final moments, while gradually releasing that stored energy into space. The cooling process is so slow that white dwarfs can remain visible for longer than the current age of the universe, creating stellar lighthouses that will continue glowing long after all the ordinary stars have burned out. The surface gravity on a white dwarf is hundreds of thousands of times stronger than Earth's gravity, creating conditions so extreme that the stellar material is compressed into exotic states of matter. Yet despite these extreme physical conditions, white dwarfs are remarkably stable and peaceful objects. They don't undergo the violent changes that characterize other stellar remnants, but instead settle into a quiet existence of gradual cooling that can continue essentially forever. Some white dwarfs exist in binary systems where they slowly accrete material from a companion star, occasionally flaring up in gentle nuclear explosions called novae when enough material accumulates on their surface. But most white dwarfs exist in solitude, cooling slowly and peacefully while drifting through space like glowing coals from a cosmic fire that burned out long ago, carrying with them the chemical legacy of stellar nucleosynthesis that enriched the galaxy with the heavy elements necessary for planet formation and life. Red giant stars expand with infinite patience across millions of years. When stars like our Sun begin to run out of hydrogen fuel in their cores, they don't suddenly change or explode. Instead, they enter a phase of gentle expansion that unfolds so gradually it would be imperceptible to countless human generations. These aging stars slowly swell to enormous sizes, sometimes growing large enough to encompass the orbits of inner planets. Yet this expansion happens with such cosmic patience that it represents one of the most peaceful transformations in the universe. As a red giant expands, its outer layers become cooler and take on the soft, warm glow that gives these stars their name. The light they emit is gentler and more diffuse than that of younger stars, spreading their luminous warmth across vast volumes of space. Despite their enormous size, red giants maintain the same steady nuclear burning in their cores that has sustained them for billions of years, just rearranged in a way that allows their outer layers to drift slowly outward like a cosmic exhalation. This expansion phase can last for hundreds of millions of years, during which the star maintains its essential character while gradually transforming its relationship with the space around it. Planets that once orbited close to the star find themselves bathed in increasingly warm light, while more distant worlds may experience their first taste of stellar warmth after billions of years in the cold outer reaches of their solar system. Eventually, red giants will gently shed their outer layers into space, creating beautiful planetary nebulae that drift outward for thousands of years. But this final exhalation is still millions of years in the future for stars just beginning their red giant phase, giving them eons to slowly adjust to their new configuration while maintaining the steady gravitational embrace that keeps their planetary systems intact. Asteroid belts drift in organized rivers of ancient debris, Between the orbits of Mars and Jupiter lies a region filled with millions of rocky fragments left over from the formation of our solar system. Rather than chaotic rubble hurtling through space, these asteroids follow predictable, well-organized orbits that create natural highways of slowly moving debris. Each asteroid maintains its own peaceful path around the Sun, taken between 3 and 6 years to complete one orbit while maintaining safe distances from its neighbors. The asteroid belt isn't the crowded, collision-filled region often depicted in science fiction. Instead, the space between individual asteroids is so vast that a spacecraft could travel through the belt without coming close to any of the rocky inhabitants. The asteroids are spread across such enormous distances that they're typically millions of kilometers apart, each one following its solitary path through space like a cosmic hermit on an eternal pilgrimage around the Sun. These ancient fragments preserve the original composition of the early solar system, having remained essentially unchanged for over 4 billion years. They represent time capsules from the era when planets were first forming, rocky building blocks that never quite managed to assemble themselves into a full-sized world, but instead remained scattered in their orbital zone, like the pieces of a cosmic puzzle that was never completed. Some asteroids follow more elliptical orbits that bring them closer to the Sun before carrying them back out to the cooler regions of the belt. Others maintain nearly circular paths that keep them at consistent distances from our star throughout their long orbital journeys, regardless of their individual characteristics. All of these rocky fragments participate in the same gentle gravitational dance that has organized their motions since the solar system's youth. The Kuiper Belt extends our solar system's peaceful realm beyond Neptune. Far beyond the orbit of Neptune lies another belt of ancient objects, but these are composed primarily of ice rather than rock. The Kuiper Belt contains thousands of small, frozen worlds that orbit the Sun in the cold outer reaches where sunlight is so faint that noon resembles twilight on Earth. These distant objects include dwarf planets like Pluto, as well as countless smaller bodies that represent some of the most pristine remnants of our solar system's formation. Objects in the Kuiper Belt follow much more distant orbits than the asteroids, taking anywhere from several decades to several centuries to complete one journey around the Sun. Their orbital periods are so long that some Kuiper Belt objects haven't completed even one full orbit since they were first discovered by human astronomers. This creates a realm where change happens on timescales that exceed human civilization, where orbital positions shift so slowly that the sky would appear essentially frozen from the perspective of any hypothetical observer. The extreme distance of these objects means they exist in a state of perpetual deep freeze, with surface temperatures that approach absolute zero. Any water on their surfaces has been frozen solid for billions of years, creating worlds of permanent winter where the seasons are measured not in months, but in geological ages. Yet even in this frozen realm, these objects maintain their orbital stability with the same gravitational precision that governs the inner solar system. Many Kuiper Belt objects exist in orbital resonances with Neptune, locked into mathematical relationships where their orbital periods are simple ratios of Neptune's orbital period. This creates a hidden harmony in the outer solar system, where gravitational forces work over millions of years to maintain stable configurations that prevent these distant objects from wandering too far from their designated orbital zones. Galactic clusters drift through space in slow-motion collisions. On the largest scales of cosmic structure, entire galaxies exist within vast gravitational communities called galaxy clusters, containing hundreds or thousands of individual galaxies bound together by their mutual gravitational attraction. These clusters move through space as single units, occasionally encountering other clusters in cosmic collisions that unfold over hundreds of millions of years. When galaxy clusters collide, the process is so gradual that individual galaxies within the clusters typically pass by each other without direct contact. The collision happens primarily between the hot gas that fills the space between galaxies, creating shock waves and turbulence that can be detected in X-ray wavelengths. These intergalactic shock waves move at speeds of thousands of kilometers per second, yet they're still gentle enough that they don't disrupt the internal structure of individual galaxies. The gravitational effects of cluster collisions can strip gas away from galaxies, removing the raw material needed for future star formation and gradually transforming spiral galaxies into more elliptical shapes. But this transformation happens so slowly that billions of years pass between the initial collision and the final structural changes, allowing multiple generations of stars to form and evolve within the galaxies, even as their parent cluster undergoes this cosmic metamorphosis. Some galaxy clusters contain thousands of individual galaxies, creating gravitational environments so complex that computer simulations require months of calculation time to model their behavior accurately. Yet despite this complexity, the overall motion of galaxy clusters through space follows predictable patterns determined by the large-scale distribution of dark matter, creating cosmic currents that carry entire communities of galaxies along paths that were established billions of years ago. Neutron stars spin with perfect precision in the cosmic dark. When the most massive stars reach the end of their lives, some leave behind neutron stars, objects so dense that a sugar cube-sized piece would weigh as much as a mountain on Earth. Despite their incredible density, these stellar remnants spin with extraordinary smoothness, some rotating hundreds of times per second, while maintaining timing precision that rivals the best atomic clocks ever built. Neutron stars are composed almost entirely of neutrons packed together at nuclear density, creating matter in a state that doesn't exist anywhere else in the universe. Their surfaces are perfectly smooth, without mountains or valleys higher than a few centimeters, because their intense gravitational fields flatten any irregularities that might try to form. This creates objects that are simultaneously the most extreme and the most perfectly spherical entities in the cosmos. The magnetic fields around neutron stars are trillions of times stronger than Earth's magnetic field, yet they maintain stable configurations that can persist for millions of years. These magnetic fields channel the neutron star's rotation energy into beams of radiation that sweep across space like cosmic lighthouses, creating the pulsars that serve as precise timekeeping beacons throughout the galaxy. Some neutron stars exist in binary systems, where they slowly spiral toward each other over millions of years. gradually losing orbital energy by radiating gravitational waves. When these systems finally merge, they create some of the most energetic events in the universe. But even these dramatic endings result from processes that unfold with mathematical precision over cosmic timescales that dwarf human experience. Void regions create cosmic meditation spaces between galaxy clusters. Between the filaments and nodes of the cosmic web lie enormous regions called voids, vast spaces that contain very few galaxies and represent some of the most peaceful and empty regions in the universe. These cosmic voids can be hundreds of millions of light-years across, creating spherical regions of space where matter is so sparse that a hypothetical traveler could journey for millions of years without encountering a single star. Within these voids, the density of ordinary matter is less than 1/10 of the average density of the universe, creating conditions that are even more empty than the space between galaxies in more typical regions of the cosmos. The few galaxies that do exist within voids are typically small and isolated, following their solitary paths through space without the gravitational influences that shape galaxies in denser regions. The emptiness of cosmic voids isn't absolute, as they still contain the same dark matter and dark energy that permeate the rest of the universe. But the absence of luminous matter creates regions where space itself seems to take on a meditative quality. Vast spheres of cosmic silence, where the usual processes of star formation and galactic evolution proceed at their most leisurely pace. These voids gradually expand as the universe continues its overall expansion, growing larger and emptier over time as the galaxies on their boundaries are carried farther apart by the stretching of space itself. This creates regions that are becoming increasingly peaceful and isolated, cosmic sanctuaries where the universe approaches its most serene possible state. Planetary rings shepherd themselves through gravitational harmony. The particles that make up planetary ring systems don't simply orbit randomly around their parent planets, but organize themselves into intricate patterns through subtle gravitational interactions that create self-maintaining structures of extraordinary beauty and complexity. These ring systems demonstrate how gravitational forces can create order from apparent chaos, establishing stable configurations that persist for millions of years. Small moons embedded within ring systems act as gravitational shepherds, using their modest gravitational influence to maintain gaps and divisions in the rings. These shepherd moons don't actively push ring particles around, but instead create zones of orbital resonance where particles are gradually nudged into stable configurations through repeated gravitational encounters that accumulate their effects over thousands of orbital periods. The individual particles within rings occasionally collide with each other, but these collisions typically result in the particles sticking together temporarily before breaking apart again due to tidal forces from the parent planet. This creates a constant cycle of aggregation and disaggregation that maintains the ring system's overall structure while allowing for subtle changes and evolution over long periods of time. Some ring systems contain spiral density waves, patterns that propagate through the ring material like ripples on a pond, created by gravitational perturbations from nearby moons. These waves move through the rings at predictable speeds, creating temporary concentrations of ring particles that appear as spiraling brightness variations when viewed from a distance, demonstrating how even the most delicate gravitational influences can create large-scale patterns in cosmic structures. Solar system debris follows predictable paths through interplanetary space. Throughout our solar system, countless small particles of dust and debris follow their own gentle orbits around the Sun, creating a tenuous medium that fills the space between planets. This interplanetary dust comes from various sources, including comet tails, asteroid collisions, and particles expelled from planetary atmospheres. Yet it all follows the same basic orbital mechanics that govern larger objects in the solar system. Most of this debris is incredibly small, consisting of particles no larger than grains of sand. Yet each piece maintains its own individual orbit around the Sun with the same gravitational precision that characterizes planets and moons. The particles gradually spiral inward toward the Sun due to various forces including radiation pressure and interactions with the solar wind. But this inward drift is so slow that it takes thousands of years for particles to migrate from the outer solar system to the inner regions. When Earth passes through regions of higher particle density, we experience meteor showers as these tiny fragments burn up in our atmosphere, creating brief streaks of light that represent the final moments of particles that may have been orbiting the Sun for millions of years. These meteor showers occur at predictable times each year as Earth follows its orbit through the debris trails left by comets, demonstrating the long-term stability of these particle streams. The zodiacal light, a faint glow visible in dark skies just after sunset or before sunrise, is created by sunlight reflecting off this interplanetary dust. This gentle illumination reveals the presence of countless microscopic particles distributed throughout the inner solar system, each one following its own peaceful trajectory through the cosmic medium that connects all the worlds in our solar neighborhood. Tidal forces create the gentlest possible cosmic massage. Throughout the universe, whenever objects orbit close enough to each other, they experience tidal forces that stretch and compress them in rhythmic cycles synchronized with their orbital periods. These forces work by creating slightly different gravitational pulls on different parts of an object, with the near side being pulled more strongly than the far side, resulting in a gentle stretching effect that flexes the object as it orbits. On Earth, we experience tidal forces from both the Moon and the Sun, which combine to create the familiar pattern of ocean tides that rise and fall twice each day. But tidal forces affect not just the oceans, but the solid Earth itself, causing the entire planet to flex slightly as we orbit the Sun and as the Moon orbits around us. This planetary flexing amounts to only a few centimeters, but it represents a cosmic massage that has been continuing for billions of years. Moons throughout the solar system experience much stronger tidal effects, particularly those that orbit close to massive planets like Jupiter and Saturn. These tidal forces can generate enough internal heat to melt ice and create subsurface oceans, as is believed to occur on moons like Europa and Enceladus. The tidal heating process works gradually and steadily, providing a constant source of energy that can maintain liquid water for billions of years. In some cases, tidal forces are strong enough to gradually synchronize the rotation of moons with their orbital periods, creating tidally locked systems where the same face of the moon always points toward its parent planet. This synchronization doesn't happen suddenly, but develops gradually over millions of years as tidal friction slowly adjusts the moon's rotation rate until it matches its orbital period perfectly. Cosmic microwave background radiation maintains perfect temperature equilibrium. Filling all of space with perfect uniformity is the cosmic microwave background radiation, the afterglow of the Big Bang that has been cooling and stretching for nearly 14 billion years. This radiation maintains a temperature of 2.725 Kelvin throughout the entire observable universe, varying by only tiny fractions of a degree from one region to another, creating the most perfect example of thermal equilibrium ever discovered. This background radiation represents the leftover photons from a time when the entire universe was as hot and bright as the surface of a star. But expansion has stretched these photons to much longer wavelengths and much lower energies. The process has been so uniform and gradual that the radiation maintains almost exactly the same temperature in every direction we look, creating a cosmic environment that's more thermally stable than any laboratory on Earth. The tiny temperature variations that do exist in the cosmic microwave background represent the seeds from which all large-scale structure in the universe eventually grew. These variations are so small that they amount to temperature differences of only a few millionths of a degree. Yet they provided the gravitational templates around which galaxies and galaxy clusters would eventually form over billions of years. The presence of this radiation means that nowhere in the universe is truly at absolute zero temperature. Even in the emptiest regions of intergalactic space, far from any stars or galaxies, the cosmic microwave background provides a minimum temperature that prevents any location from becoming completely cold. This creates a universe where warmth, however faint, is truly universal and eternal. Lagrange points create gravitational oases of perfect stability throughout any system containing two massive objects in orbit around each other. There exist 5 special locations called Lagrange points, where the gravitational forces from both objects combine in such a way that smaller objects can maintain stable positions relative to the two larger masses. These points represent solutions to the complex mathematical problem of three-body orbital mechanics, creating cosmic parking spaces where objects can remain stationary relative to the orbiting system. The most stable of these points, known as L4 and L5, form equilateral triangles with the two primary masses, creating regions where small objects can orbit with the same period as the larger system, while maintaining fixed positions relative to both primary objects. These points are so stable that they can collect and hold populations of asteroids for millions of years, creating gravitational oases in the otherwise dynamic environment of orbital mechanics. Earth and the Sun create their own set of Lagrange points, and several space missions have taken advantage of these locations to position satellites and telescopes in spots where they can maintain their positions with minimal fuel consumption. The James Webb Space Telescope orbits around the L2 point, located beyond Earth's orbit, where it can observe deep space without interference from Earth's heat and light, while remaining in constant communication with ground-based controllers. Other Lagrange point systems throughout the solar system collect natural debris and provide stable environments for long-term astronomical observations. Jupiter shares its orbital path with thousands of asteroids located at its L4 and L5 points, called Trojan asteroids, demonstrating how these gravitational oases can maintain stable populations of objects for billions of years, while the larger system continues its orbital dance around the Sun. Stellar nurseries incubate new suns in perfect cosmic wombs. Throughout the galaxy, vast molecular clouds provide the most nurturing possible environments for the formation of new stars, creating cosmic nurseries where the process of stellar birth unfolds with infinite patience and care. These clouds contain the coldest and densest concentrations of matter in the galaxy, with temperatures just a few degrees above absolute zero and densities that can exceed thousands of particles per cubic centimeter. Within these stellar nurseries, gravity works so gently that the collapse process leading to star formation can take millions of years to complete. The molecular clouds are so large that they can give birth to thousands of stars simultaneously, creating stellar associations where groups of stars form together and begin their lives as cosmic siblings, sharing similar ages and compositions. The process of stellar formation is remarkably inefficient, with most of the material in a molecular cloud being dispersed back into space by stellar winds and radiation pressure from the newly formed stars. This means that stellar nurseries are self-limiting, gradually destroying the very conditions that allowed them to form stars in the first place, but doing so over such long timescales that they can continue producing new stars for millions of years. Young stars within these nurseries are often surrounded by protoplanetary disks, flat rings of gas and dust, where planets will eventually form. These disks can persist for millions of years, providing stable environments where planetary formation can proceed gradually through the gentle accumulation of dust grains into larger and larger objects, eventually creating the diverse families of planets we observe around mature stars throughout the galaxy. The galaxy. Multiple star systems create celestial symphonies of perfect orbital harmony. While our solar system contains only one star, most stellar systems throughout the galaxy consist of multiple stars bound together in gravitational partnerships that can persist for billions of years. These multi-star systems demonstrate some of the most elegant examples of celestial mechanics, with stars orbiting around their common centers of mass in patterns that remain stable across cosmic time. In binary star systems, two stars dance around each other in orbits that can range from incredibly tight, with orbital periods of just hours, to extremely wide, taking thousands of years to complete one cycle. The closest binary systems are so tightly bound that the stars nearly touch each other, creating egg-shaped stars that are tidally distorted by their mutual gravitational embrace. Yet even these extreme configurations maintain their orbital stability, with each star following its prescribed path with mathematical precision. Some multiple star systems contain 3, 4, or even more stars arranged in hierarchical configurations, where smaller groups orbit around larger groups. These systems create incredibly complex gravitational environments yet they maintain their stability through the same fundamental principles that govern simpler two-body systems. The stars in these systems age together, evolve together, and sometimes transfer material between each other in gentle stellar embraces that can continue for millions of years. The light from multiple star systems often varies in predictable patterns as the stars eclipse each other from our perspective, creating natural cosmic lighthouses that pulse with the rhythm of their orbital periods. These eclipsing binaries serve as precise cosmic clocks, marking time with stellar precision across the galaxy and providing astronomers with some of the most accurate distance measurements possible for objects beyond our solar system. Galactic magnetic fields thread through space like invisible cosmic silk. Our galaxy is permeated by magnetic fields that extend across thousands of light years, creating an invisible infrastructure that guides the motion of charged particles and influences the formation of stars and planets. These magnetic fields are incredibly weak by terrestrial standards, thousands of times weaker than the magnetic field of a simple refrigerator magnet. Yet they extend across such vast distances that they contain enormous amounts of energy and help organize the structure of the entire galaxy. These cosmic magnetic fields follow the spiral structure of the galaxy, threading along the spiral arms like invisible silk fibers that connect distant regions of space. As the galaxy rotates, these magnetic field lines are stretched and twisted, creating complex patterns that evolve slowly over millions of years while maintaining their overall connection across galactic scales. Charged particles from cosmic rays and stellar winds follow these magnetic field lines like traffic following invisible highways, spiraling around the field lines as they travel through interstellar space. This creates cosmic particle streams that can transport energy and matter across vast distances, connecting different regions of the galaxy through invisible channels of magnetic influence. The interaction between these galactic magnetic fields and the solar wind creates the boundary of our heliosphere, the region of space dominated by our sun's influence. As we travel through the galaxy, our solar system encounters different magnetic field orientations and strengths, creating subtle variations in our cosmic environment that change over timescales of millions of years as we complete our orbit around the galactic center. Cosmic dust grains serve as seeds for the formation of worlds. Throughout interstellar space, tiny particles of dust smaller than the width of human hair drift on currents of starlight and stellar wind, serving as the fundamental building blocks for all solid objects in the universe. These microscopic grains are composed of elements forged in the hearts of ancient stars, including carbon, silicon, and iron, mixed with ices of water, methane, and other simple molecules that condense in the cold depths of space. When these dust grains encounter each other in the dense environments of stellar nurseries, they begin to stick together through electrostatic forces and van der Waals interactions, gradually building up into larger and larger particles over millions of years. This process of accretion is incredibly gentle, with dust grains coming together like cosmic snowflakes that accumulate so slowly that the growth of planetary building blocks is measured in geological time. The surfaces of these dust grains serve as catalysts for chemical reactions that cannot occur in the gas phase, allowing complex organic molecules to form in the cold vacuum of space. These grain surface reactions proceed slowly over thousands of years, building up layers of organic compounds that can eventually be incorporated into comets, asteroids, and planets, carrying the chemical complexity of interstellar space into newly forming solar systems. As dust grains grow larger through accretion, they begin to settle toward the midplanes of protoplanetary disks, creating dense layers of solid material where planets can eventually form. This settling process is driven by the gentle drag forces exerted by the surrounding gas, causing solid particles to spiral slowly inward while maintaining their circular orbits around the central star, creating the perfect conditions for planetary formation to begin. Helioseismology reveals the sun's gentle internal rhythms. Deep within our sun, pressure waves created by convective turbulence travel through the stellar interior, bouncing off the solar core and creating standing wave patterns that cause the entire star to ring like an enormous bell. These solar oscillations are incredibly subtle, causing the sun's surface to move up and down by distances of only a few meters. But they occur with such regularity that they provide a window into the sun's internal structure and dynamics. The sun oscillates in millions of different modes simultaneously, each with its own frequency and pattern, creating a complex symphony of stellar vibrations that has been playing continuously for billions of years. Some of these oscillations have periods of just a few minutes, while others take hours to complete one cycle. But all of them maintain their characteristic frequencies with remarkable stability over long periods of time. By studying these solar oscillations, astronomers can map the internal structure of the sun with extraordinary precision, revealing details about the temperature, density, and rotation rate at different depths within the stellar interior. This technique, called helioseismology, has shown that the sun's core rotates more slowly than its surface layers, creating internal shear zones where different parts of the star move at different rates. The discovery of these solar oscillations has revealed that our sun is a much more dynamic and complex object than previously imagined. Yet this complexity manifests itself through gentle, predictable variations that demonstrate the fundamental stability of stellar structure. Even as the sun undergoes constant internal motion and adjustment, it maintains the steady energy output that has sustained life on Earth for billions of years. Planetary atmospheres create protective cocoons around their worlds. The thin layers of gas that surround planets serve as much more than simple collections of atmospheric molecules, creating complex protective systems that regulate temperature, shield surfaces from harmful radiation, and sometimes provide the chemical environments necessary for life to flourish. These atmospheric envelopes demonstrate how even the thinnest layers of gas can create dramatically different environments on otherwise similar worlds. Earth's atmosphere creates a greenhouse effect that maintains surface temperatures warm enough for liquid water to exist, while also providing protection from ultraviolet radiation through its ozone layer and from meteorite impacts through atmospheric friction that causes small debris to burn up harmlessly. This atmospheric protection operates continuously and automatically, requiring no maintenance or intervention while providing essential services that make our planet habitable. Other planets demonstrate the dramatic effects that different atmospheric compositions can have on planetary environments. Venus has a thick carbon dioxide atmosphere that creates such an intense greenhouse effect that surface temperatures exceed 450 degrees Celsius, while Mars has such a thin atmosphere that it provides little protection from temperature extremes or radiation, creating a harsh environment where liquid water cannot exist on the surface. The giant planets have atmospheres that extend for thousands of kilometers below their visible cloud tops, creating pressure and temperature conditions that gradually transition from gas to liquid to solid phases without clear boundaries. These deep atmospheres contain their own weather systems and circulation patterns that can persist for decades or centuries, creating atmospheric features like Jupiter's Great Red Spot that demonstrate the remarkable stability possible in planetary atmospheric systems. Gravitational lensing creates cosmic magnifying glasses from massive objects. Throughout the universe, the gravitational fields of massive objects like galaxies and galaxy clusters bend the paths of light rays passing near them, creating natural telescopes that can magnify and focus light from even more distant objects. This gravitational lensing effect transforms some of the most massive structures in the universe into cosmic optical instruments that allow us to see farther into space than would otherwise be possible. When light from a distant galaxy passes near a massive galaxy cluster, the cluster's gravitational field acts like a giant lens, bending the light rays and creating multiple images of the background galaxy that can appear as arcs, rings, or distorted shapes around the lensing cluster. These gravitational lenses can magnify the light from background objects by factors of 10 or even 100, making faint, distant galaxies bright enough to study in detail. The lensing effect is perfectly predictable based on Einstein's theory of general relativity, allowing astronomers to use these natural cosmic telescopes to study the distribution of both ordinary matter and dark matter in the lensing objects. By carefully analyzing how light is bent as it passes through gravitational fields, scientists can map the invisible mass that creates the lensing effect with extraordinary precision. Some gravitational lenses create nearly perfect Einstein rings, circular or arc-like images that form when the lensing object, the background source, and the observer are nearly perfectly aligned. These cosmic alignments are relatively rare, but when they occur, they create some of the most beautiful and scientifically valuable observations possible, demonstrating how the geometry of space-time itself can be used as a tool for astronomical discovery. Stellar winds carry the breath of stars across interstellar space. All stars emit streams of charged particles that flow outward from their surfaces at speeds of hundreds of kilometers per second, creating stellar winds that carry matter and energy into the surrounding interstellar medium. These winds are driven by the intense radiation pressure and magnetic fields in stellar atmospheres, creating a continuous outflow that can persist for billions of years throughout a star's lifetime. Our sun produces a solar wind that extends throughout the entire solar system, creating a bubble of solar influence called the heliosphere that protects us from some forms of cosmic radiation while carrying away about 1 million tons of solar material every second. Despite this seemingly enormous mass loss, the Sun is so massive that it can maintain this stellar wind for billions of years without significantly affecting its overall structure or energy output. More massive stars produce much stronger stellar winds that can carry away significant fractions of the star's mass over their lifetimes, sometimes completely stripping away their outer layers and exposing their hot inner cores. These stellar winds enrich the interstellar medium with heavy elements produced by nuclear fusion in stellar cores, gradually increasing the chemical complexity of the galaxy over cosmic time. When stellar winds from different stars encounter each other in space, they can create shock waves and turbulent mixing zones where the material from multiple stellar sources combines and interacts. These wind-wind interactions can trigger the compression of nearby gas clouds, sometimes initiating new episodes of star formation in a process that connects the life cycles of different generations of stars through the medium of their stellar winds. Cosmic ray particles carry messages from distant stellar explosions. Throughout the galaxy, high-energy particles called cosmic rays travel at nearly the speed of light, carrying with them the signatures of the violent stellar events that accelerated them to such incredible energies. These particles represent messengers from some of the most energetic phenomena in the universe, including supernova explosions, neutron star collisions, and the regions around black holes, where matter is accelerated to relativistic speeds. When cosmic rays strike Earth's atmosphere, they create cascades of secondary particles that rain down on the surface, providing a constant, gentle bombardment that has been occurring throughout Earth's history. These cosmic ray showers are typically harmless to life on the surface, but they create a background of natural radiation that can be detected by sensitive instruments and contributes to the natural mutation rate that drives biological evolution. The paths that cosmic rays follow through the galaxy are influenced by magnetic fields, causing them to spiral around magnetic field lines and take indirect routes from their sources to Earth. This means that cosmic rays can spend millions of years traveling through the galaxy before reaching us, carrying information about stellar explosions that occurred long ago in distant regions of space. Different types of cosmic rays carry information about different kinds of astronomical objects and events. The most energetic cosmic rays may come from sources outside our galaxy entirely, representing particles that have traveled for millions of years across intergalactic space to bring us news of events in distant galaxy clusters or active galactic nuclei that are too far away to study through any other means. Planetary magnetic fields deflect cosmic radiation with invisible shields. Many planets throughout the solar system generate their own magnetic fields through the motion of electrically conducting fluids in their interiors, creating protective magnetic bubbles that deflect charged particles from space and shield their surfaces from harmful cosmic radiation. These planetary magnetic fields operate like invisible force fields, creating safe havens where atmospheres can persist and life can potentially develop without being sterilized by high-energy particles from space. Earth's magnetic field is generated by the motion of molten iron in our planet's outer core, creating a complex dipolar field that extends thousands of kilometers into space and creates the magnetosphere that protects us from the solar wind and cosmic rays. This magnetic shield is not perfectly stable but varies in strength and orientation over time, occasionally reversing its polarity in events that occur every few 100,000 years on average. Other planets with strong magnetic fields, like Jupiter and Saturn, create even more extensive magnetospheres that can trap charged particles from space and accelerate them to high energies, creating radiation belts that can be hazardous to spacecraft passing through them. These planetary magnetic fields interact with the solar wind to create complex boundary layers where solar and planetary magnetic field lines reconnect and create auroras in the planet's upper atmosphere. Mars, which lacks a strong global magnetic field today, may have had such a field in the past that helped protect a thicker atmosphere from being stripped away by the solar wind. The loss of Mars's magnetic field billions of years ago may have contributed to the gradual erosion of its atmosphere and the transformation of the planet from a potentially habitable world to the cold, dry desert we see today. Oort cloud objects preserve pristine samples from the solar system's birth. Far beyond the orbit of Neptune, at distances approaching halfway to the nearest star, lies a vast spherical shell of icy objects called the Oort cloud, containing trillions of comet nuclei that represent some of the most pristine and unaltered material from the solar system's formation. These distant objects exist in a state of deep freeze that has preserved their original composition for over 4 billion years, creating a cosmic library of information about the conditions that existed when our solar system was young. The objects in the Oort cloud follow extremely elongated orbits that can take millions of years to complete, spending most of their time in the cold darkness at the very edge of our solar system's gravitational influence. Occasionally, gravitational perturbations from passing stars or molecular clouds can nudge some of these objects into new orbits that bring them into the inner solar system, where they become visible as long-period comets with orbital periods of thousands of years. When Oort cloud comets approach the Sun, they begin to sublime and release the gases and dust that have been frozen in their nuclei since the solar system's formation. This process provides astronomers with direct samples of the primordial materials that were present in the outer regions of the solar nebula, allowing detailed studies of the chemical and isotopic composition of matter that predates the formation of the planets. The Oort cloud itself may contain more mass than all the planets combined, distributed among countless small objects that range in size from a few kilometers to hundreds of kilometers in diameter. This vast reservoir of icy material represents the outermost boundary of our solar system's sphere of influence, creating a buffer zone between our local planetary system and the interstellar medium that lies beyond. Galactic rotation creates spiral density waves that organize stellar formation. As our galaxy rotates, it doesn't spin like a solid wheel, but instead follows a more complex pattern where different regions rotate at different speeds, creating spiral density waves that propagate through the galactic disk like slow-motion traffic jams. These density waves compress the interstellar medium as they pass, triggering episodes of star formation that light up the spiral arms and create the beautiful spiral patterns we see in galaxies throughout the universe. And now, as we reach the end of our gentle journey through the cosmos, let your mind settle into the profound peace that surrounds us all. We've drifted together through stellar nurseries and galactic spirals, through the whispered songs of pulsars and the silent dance of dark matter. Each fact we've shared tonight carries with it the same message: that the universe, in all its vastness, operates with a patience and gentleness that exceeds our deepest capacity for calm. From the cosmic microwave background that wraps everything in ancient warmth to the gravitational waves that massage reality itself with touches softer than a feather, space itself seems designed for tranquility. So as you close your eyes tonight, remember that you are held within this cosmic embrace, breathing the same stellar elements that have been cycling peacefully through the universe for billions of years, part of a story so vast and so gentle that even sleep becomes a form of cosmic meditation.